Have you ever traveled by road to a hilly area, that is, to a higher altitude place? Did you carry chips packets with you? Have you observed that if you go to higher altitudes, the chips packets start to expand and at times they even burst? Well, why does that happen? Think about it. So we have a person, he's running. So let's count the number of times the person hits the boundaries in 1 minute. 1, 2, 3, 4, 5, 6, 7, 8. So in 1 minute, the person touches the boundaries 8 times. Now, if the person runs at the same speed, that is, the speed of the person remains constant and he has to cover double the distance in the same time, that is in 1 minute only, the person now has to cover double the distance and he's running at the same speed. How many times will he touch the boundaries? Let's count. So 1, 2, 3, 4. So now if he has to cover double the distance, he touches the boundaries half number of times. So let's compare this. The person in both the cases is running at the same speed. In 1 minute, he touches the boundaries 8 number of times, and if he has to cover double the distance, the number of times he touches the boundaries is reduced to half. So by the time he covers one distance, he has already covered double the distance. So you see that the distance covered is related to the number of hits per unit time. If the distance covered is less, that is, if he had to cover lesser distance, the number of hits per unit time increases. And if the distance covered that he had to cover is more, the number of hits per unit time decreases if the speed of the person remains constant. Similarly, we have distance covered is inversely proportional to the number of hits per unit time. This means greater is the number of hits per unit time, lesser is the distance covered. So this also is the case when the speed remains constant. In physics, you must have studied that pressure at the same height remains the same. So if an experiment is performed, in this we have different shaped tubes. Now, if a liquid is poured in these tubes, all the tubes are different in shapes. So it is observed that they take the same heights, irrespective of their shapes. The height in all the tubes is the same. So by this we know that the pressure at the same height remains the same. This concept was used by a scientist named Robert Boyle. He performed an experiment which was known as Boyle's experiment. He performed the experiment in 1662. Let's see what he performed. He took a J-shaped tube. A gas is enclosed in this tube. And this is the scale that he used to measure the volume of the gas enclosed. Now he added mercury in the tube. So let's see what happens. As he added mercury, the volume of the gas enclosed reduces. So now the volume enclosed is 60 centimeter cube. This is the pressure exerted by gas, and this is the atmospheric pressure. We know that pressure at same heights remains the same. So at this point, this is the pressure of gas. At this point, the pressure exerted is the atmospheric pressure, which is 760 millimeters of mercury. This remaining same, he added more mercury so as to make the volume of the gas enclosed half. So when he added more mercury, he saw that the volume reduced to half. Now it occupies 30 centimeter cube. This is the pressure exerted by gas. And when he calculated the pressure on the other side, he observed that the pressure was the atmospheric pressure plus 760 millimeters of mercury. So now the pressure was 2 times 760 millimeters of mercury. Now this setup remaining the same, he added more mercury so as to make the volume of the gas enclosed 1/3. So when he added more mercury, the volume becomes 1/3, that is 20 centimeter cube. This is the pressure exerted by gas. Pressure at same height remains the same. So on the other side, when he calculated, the pressure was the pressure of atmosphere plus 1520 millimeters of mercury. So the overall pressure is 3 times 760 millimeters of mercury. So he observed, as the pressure becomes 3 times, the volume becomes 1/3. So he concluded that if the pressure was doubled at constant temperature, all the calculations, the entire experiment which Boyle had performed was at a constant temperature. And he was able to observe that when the pressure was doubled, the volume of the gas became half the original volume. And as the pressure was tripled, the volume became 1/3 the original volume. So as the pressure was doubled, volume became half. As the pressure was tripled, volume became 1/3. So based on this, as we have seen already from this experiment, that is a gas enclosed in a container. In 9 seconds, there are 9 hits. So there is 1 hit per second. If the volume is reduced to half, so in the same time, that is in 9 seconds only, there are 18 hits. So as the volume is halved, the pressure doubles. So based on his experiment, Boyle gave the law. His law states that the volume is inversely proportional to pressure, temperature remaining constant. This is something that we have seen through the person running. So there we had the distance covered is inversely proportional to the number of hits per unit time, the speed remaining constant. So in Boyle's law, the distance covered is the volume occupied by the gas, the number of hits per unit time is the pressure of the gas, and speed is the temperature. So according to Boyle's law, the volume of the gas is inversely proportional to pressure at temperature remaining constant. So the Boyle's law states that the volume of a given mass of gas, so the law holds for a particular gas. So for a given mass of gas, the volume is inversely proportional. So you have to keep in mind that the volume is inversely proportional to pressure at constant temperature. So the law holds only at a constant temperature for a particular gas. So from the law we have that the volume is inversely proportional to pressure, temperature remaining constant for a particular gas. So to remove the proportionality sign, we introduce a constant. So we get volume is equal to constant divided by pressure. Now if we take pressure on the other side, we get pressure into volume is equal to constant. So the product of pressure and volume is a constant value. And this is the Boyle's law. So for a particular gas, the product of pressure and volume at a constant temperature is constant. So let's see a small experiment. So a gas is enclosed in a container. Now we'll increase the pressure, which can also be seen through this pressure gauge. We increase the pressure from top. So as the pressure is increased, the volume decreases. So you see the values. As the pressure is increasing, the volume which is enclosed in the container is reducing. And you see that the product of pressure and volume is constant. So as the pressure increases, volume decreases, but the product of pressure and volume is always constant. So from this, we can also plot the values. So if we draw a graph between the pressure and volume of a gas, we get a curve, which shows that as volume increases, the pressure decreases. We know that according to Boyle's law, pressure is inversely related to volume. Or we can also say that volume is inversely related to pressure. So as the volume increases, the pressure decreases. Now let's say if this 1 by V is X So we get that pressure is directly proportional to 1 by V, which is X. So we get pressure directly proportional to X. And over here, X is 1 by V. So pressure is inversely proportional to volume and pressure is directly proportional to 1 by volume. So if we plot a graph between 1 by volume and pressure, we get a straight line. So you see that as 1 by volume increases, the pressure increases. So pressure is directly proportional to 1 by volume. Since these graphs are plotted at constant temperature, so these are also known as isotherms. Iso means same, therm means for temperature. Since Boyle's law is valid for a gas at constant temperature, so these graphs are known as isotherms. That means the temperature remains constant. The pressure of a gas increases with the increase in volume. Is it true or false? So from Boyle's law, we know that pressure is inversely related to volume. So as volume increases, pressure decreases. So with the increase in volume, pressure decreases. So the pressure of a gas decreases with the increase in volume. So the statement that we have is false. It does not increase, it decreases with the increase in volume. From Boyle's law, we saw that PV, that is the pressure into volume of a gas, is constant. Let us denote this constant by K, and we know this is valid for a particular gas at a constant temperature. So if we have the initial conditions, say at some initial pressure and at initial volume, the product comes out to be K. The final pressure of the gas is P2 and the final volume is V2. Again the product is constant, which is K. So we get that P1 into V1 is equal to P2 into V2. So initial pressure into initial volume is equal to final pressure into final volume, which is K and which is a constant. So from this we get that these two quantities are same. So P1 V1 is equal to P2 V2. That is, the initial pressure of a gas for a particular gas and the initial volume of a particular gas is equal to the final pressure of a particular gas into the final volume of that gas, and temperature remains constant. Now let's explain the Boyle's law in terms of kinetic theory. So we know, we have seen that pressure and volume are inversely related. So what is happening here is, as external pressure increases, the internal pressure has to increase. This means the number of hits per unit time has to increase, and this is possible only when the volume is decreased. As the volume is decreased, the number of hits per unit time increases and the pressure increases. So let's recall. As outside pressure increases, to balance it, the inside pressure has to increase. This means the number of hits per unit time has to increase. For the same number of particles, this is possible only when the volume decreases. When the volume decreases, the number of hits per unit time increases. So we get, as the pressure increases, the volume decreases. Similarly, the vice versa case, if we decrease the external pressure, to balance it, the internal pressure has to decrease. This means the number of hits per unit time has to decrease. Now again, we have the same number of molecules. So to reduce the number of hits per unit time, they should travel a greater distance. This is possible only when the volume increases. As the number of particles remain the same, so to get number of hits per unit time lesser, they should travel a greater distance. This means the volume increases. So as pressure decreases, the volume increases. So now, did you find an answer to why the chips packets burst when they are taken to higher altitudes? Okay. So this follows the Boyle's law. When we go to a higher altitude, the outside pressure is less. So to balance it, the pressure inside the chips packet should also be reduced. So now the inside pressure has to be less. How is that possible? By Boyle's law, if the inside pressure is less, the volume increases. And if the volume increases, the chips packet expand in size, and at times they expand to such an extent that they burst. So why do the chips packets burst when taken to higher altitudes? At higher altitudes, the outside pressure is less. So to balance it, the inside pressure, that is the pressure inside the chips packets, that has to decrease. So by Boyle's law, if the inside pressure, that is the pressure inside the chips packets, is less, the volume has to increase. As the volume increases, the chips packets expand in size, and at times they expand to such an extent that they burst. So this is the reason why the chips packets burst when they are taken to higher altitudes. You use Boyle's law even when you are breathing. So while breathing, there is a relationship between the volume and the pressure. While breathing in, we lower the diaphragm. When we lower the diaphragm, the volume inside increases. So by Boyle's law, as the volume inside increases, the pressure decreases. So the inside pressure is less, and so outside air flows in. So this is how we breathe in. So we lower the diaphragm, the volume increases, pressure decreases. So to balance it, the outside air, from outside, it moves in. This is how we breathe in. So while breathing out, what happens? We push the diaphragm up. As we push the diaphragm up, the volume inside decreases. So by Boyle's law, as the volume decreases, the pressure increases. So to balance it, the air inside flows outside. Since the inside pressure is more, so air from inside flows outside, and this is how we breathe out. So we even use Boyle's law during breathing. Now let's try to solve a question. At a constant temperature, the volume of a gas was found to be 400 centimeter cube at a pressure of 760 millimeters of mercury. If the pressure of the gas is increased by 25%, what should be the new volume? Okay, now let's write down the data that we are provided. So we have the initial pressure, which is 760 millimeters of mercury. And the final pressure, we know that the pressure is increased by 25%. This means that if this is the initial pressure, we increase the pressure by 25%. So what do we get? We get 125 P1 by 100. So if we divide this by 25, we get 5 P1, 25 5s are 125, and 25 4s are 100. So this is the final pressure. We need not write this for 760 millimeters of mercury because this will make the calculations lengthier. Now we are given that the initial volume is 400 centimeter cube. And we have to find out the final volume. So now, we know that the Boyle's law says that the initial pressure of the gas into initial volume is equal to final pressure into final volume. So if we solve this, so let's try to solve this. So initial pressure is P1. Initial volume is 400. Final pressure, let's write it in terms of P1. We have 5 P1 by 4. And we have to find out the final volume, which is V2. So if we calculate V2 from this, We can cancel out P1 from both the sides. So we get V2 is equal to 400 into 4 divided by 5. So this we can cancel out again. So we get 320. 8 4s are 32. So we get 320 centimeter cube. Had we substituted the 760 instead of P1, we would have just increased the calculations. So we let the values remain in terms of P1. So what do you observe here? As the pressure increases, so the final pressure has increased, so the final volume decreases.